This is a deeper dive into the database connectivity with MapleFlow that we presented in an earlier demo. We'll go through the process of loading a JDBC driver for Microsoft Access and setting up the SQL queries we used in the MapleFlow commands to connect to a database, extract data from it for use in MapleFlow calculation document, and then export results from the calculations to another database. All the work is done in Maple, where we can develop and test the routines before deploying them to MapleFlow. For this demonstration, we're using the UCAN Access open source driver, but there are many available JDBC drivers for Access and other database management systems that can be implemented in the same way as I'm showing here. First, I download the UCAN Access files into a local folder so it can be accessed by Maple. Next, I'm going to use Maple's database package to load the driver. Like every other Maple package, the database package is a module. It's a means of packaging software functions and data structures as a component that integrates readily with the rest of the software architecture. I'm going to use the long form module:-export syntax to call the functions. This will keep things consistent and self-explanatory for reasons that will become apparent later. So, for this step, I'm using the database:-load driver command, and I'm assigning it to a variable. The reason for this is because not only are modules used by our developers, Maple itself can generate modules as a result of an executed process. And that's what's happening with this command. It returns a module and assigns it to the variable. I can now find out what it provides by using the exports command. Here we see two commands. One to open a connection to an Access database through the JDBC driver, and one to close it. We'll use the module export syntax to open the connection to a named database. In this case, it's a fairly simple list of product information from a supplier of steel beams. In Access, it looks like this, with a product specification in the first column and its associated properties in each row. Note that I'm assigning this command to a variable because it too returns a module that contains a set of commands to allow me to query the database. Again, I can use exports to see these commands. For example, we can find what tables are available in the database. In this case, there's just one. We can also find the column headings, which will be useful later. But probably the most important command is execute query, which allows us to set up SQL queries and send them to Access for retrieving the data we need. For this example, we want to search the database for a certain specification code, in this case W10 by 54, and return all the parameters in the row for that product. Again, I'm using the module export syntax to set up the query, and I'm assigning the result to another variable because, as you might guess, it returns another module. This module contains the results from the query in a data structure, along with a set of commands to explore it. This includes getName that returns the name of the entered column number. We can also find out how many rows have been returned. Since there should only be one result from our search, we see that there is indeed only one row. However, if I attempt to find the corresponding value for that column, I get an error. This is because there's a hidden cursor within the data structure that can be positioned at a row of interest. By default, this is set to row 0, not row 1. The next command moves the cursor up one row, and now we can get the value from that column. This feature is a little painful for a simple result like this, but it's very powerful for more complex data structures. These are all the elements we need to put a set of commands together that can be readily implemented by the MapleFlow user. In Maple, we can create a set of procedures that use these basic commands to load the JDBC driver and connect to the Access database. Then query the database and return the parameters for use in a MapleFlow calculation. We can test these commands in Maple to make sure they work as expected. And then we can copy and paste the procedures into the code editor in MapleFlow. Now we can call the commands in a calculation sheet and select different beam specifications to load in the parameters and perform the beam loading calculations in this document. This is very useful for testing and making any adjustments to the code before converting them to a library package for wider deployment. Once we're happy with the code in MapleFlow, we can go back to Maple to create a library of the procedures, essentially turning them into a module that can be loaded into MapleFlow without exposing the source code. Again, I won't go into the details of the necessary commands to do this, but notice that we've introduced another procedure into the library. This is export params. This allows the user to export calculation results into another Access database that only captures the results from every calculation performed, and also logs whether or not they pass the design constraints in the calculation sheet. Once the module is created, there are a couple of commands that turn the module into a library file that can now be deployed and loaded into MapleFlow. This library file can be copied into the MapleFlow lib directory and can be loaded into the MapleFlow document using the with command. We can test the commands by selecting different beam specs and drive the calculation with their parameters. Note that in this document there are two factors that are calculated to determine if the results from the calculations are within the limits defined by a design standard. These are the torsional capacity, TF cap, and the bending capacity, BM cap. These factors can be used to test the results at the end of the calculation sheet. If either is greater than 1, the design fails. We can then use this to store the main results in a design database in Access. In this database there are two tables, one for those that passed and one for those that failed. And since there are many iterations of the same calculation, each entry is timestamped. In this way, the progress of the design process for this stage can be monitored and managed, allowing the design team to get the best possible design while maintaining traceability in an integrated, automated workflow.